Hello, everyone. Today, I welcome you all to this webinar on the photonic integrated circuit design and simulation using our electro-optic circuit simulator tool known as OptiSPICE. During this webinar, we will be showcasing how you can leverage the foundry PDK building blocks to build your PIC design using our OptiSPICE tool and characterize the performance of your PIC before sending it for fabrication. During this webinar, we will talk about the variety of simulation tools OptiWave Suite has to offer. We will talk about the PIC design and simulation journal workflow using our OptiWave tools. We will talk about the OptiSPICE electro-optic circuit simulator tool and its capabilities. Then we will discuss in brief about the difference between the two versions of OptiSPICE simulator, that is OptiSPICE standalone and OptiSPICE plugin. Later, we will talk in detail about the PIC design example, which is the LiDAR application, its technology, and how we can design and simulate it using OptiSPICE plugin tool by leveraging standardized building blocks from a foundry PDK. Then we will discuss how we can use another OptiWave system level simulator tool known as OptiSystem for building LiDAR systems. And towards the end, we will quickly go through the database of OptiWave tutorial, training videos, and references. OptiWave has been pioneering the development of innovative photonic design automation software. We have been in the industry for more than 30 years now, with our presence in more than 80 countries. We have more than 15,000 active users with over 3 million valuations and 7,000 plus active accounts. Our tools have been widely used by the researchers, engineers, and students worldwide, leading to over 12,000 citations. OptiWave offers system-level simulator tools like OptiSystem, which is a cutting-edge and a powerful flagship tool, allowing users to simulate all kinds of optical links and complex systems by making use of a vast component library with over 600 components and a wide set of already building examples. Then we have OptiSPICE tool, which is a circuit or chip-level electro-optic circuit simulator that provides a platform to simulate and analyze integrated circuits incorporating both electrical as well as optical components. So OptiSPICE basically allows users to run electrical as well as optical simulations on a same platform in a same environment. OptiWave also offers component-level simulator tools like OptiFDTD, which allows comprehensive simulation and analysis of photonic devices, allowing researchers and engineers to model complex interactions of light and photonic structures, exploring both linear as well as nonlinear phenomena. Then we also offer OptiBPM, which simulates light propagation through any complex waveguide medium, both isotropic and anisotropic, allowing to perform switching, coupling, multiplexing, and demultiplexing of optical signals in photonic devices. Then we also offer OptiGrading, which can be used to simulate fiber Bragg gradients. We offer OptiFiber, which uses numerical mode solvers and other models specialized to fibers for calculating dispersion, losses, and birefringence during the propagation in fibers. Also, we offer OptiMode, which empowers users to thoroughly examine various waveguide structures, calculate supported modes, and determine key characteristics such as mode profiles and effective indices. Then last but not the least, OptiWave also offers a testing level simulation tool known as OptiInstrument, which is an optical system testing software tool built in collaboration with Expo, which allow researchers or engineers to easily communicate with their various instruments using remote control scripts. It helps the users to set equipment parameters, characterize passive or optical components, automate the testing process of the chips, and extract and save genetic signals for post-processing. These are a few of our key customers with whom we are working in close collaboration. Now, let's discuss about the PIC design and simulation workflow here. So generally, there are two methods to run PIC simulations using our OptiWave suite. In the first approach, we use parameterized GDS2 mask layouts from the device library. It can be either from a foundry or you can have your own mask layouts. Using those mask layouts of the building blocks, you can generate a PIC layout. You can generate a schematic of your photonic integrated circuit. Then from that layout, you can extract the netlist. And this netlist is nothing but a text file which contains information about all the components used in this layout. So it will list the components. It will also tell about the ports, whether electrical or optical ports, and also it will tell about the connections established between these components. So once you have your PIC netlist, then you can generate a PIC test bench setup wherein you will connect your this netlist component with other components like lasers, visualizers, terminators, and other electrical components to run your simulation. For running the simulation, you can use either OptiSPICE or OptiSystem, and then do the analysis of your PIC simulation. Now, if your PIC is performing as per your target, then that's good. If not, you can iterate over it until, and you can resimulate your structure, build the mask layouts, and go through this process again until your PIC output metrics are optimized and ready for fabrication. The other approach is to use building blocks from the parameterized compact model library, and you can directly use these components because they are optimized, and you can directly use them for PIC simulation using our tools. In this webinar, we will take the former approach where we will use the parameterized GDS2 mask layouts and use them for the PIC simulation. Now, let me give you a brief overview on the OptiSPICE circuit simulator tool, which is based on the SPICE engine, and it runs optoelectronic circuit simulations based on modified nodal analysis. It basically provides the user an integrated platform to carry out both electrical and optical simulations within the same environment. It is based on self-consistent solutions with Newton-Raphson iterations. OptiSPICE has a set of linear and nonlinear electrical models. OptiSPICE has a device library with wide range of multi-mode, multi-channel, bidirectional linear devices such as splitters, joiners, circulator, etc., as well as the nonlinear optical models such as lasers, optical fibers, etc. Now, OptiSPICE also allows to model the thermal behavior of the devices. Therefore, it is a powerful tool to simulate the active devices such as traveling wave resonators, Mach-Zehnder modulators, etc. OptiSPICE allows to run the frequency domain solutions as well as time domain solutions, and also it allows to run wavelength sweeps. OptiSPICE allows users to generate the electrical S parameters of their optical circuit. So, for instance, if there are any electrical engineers who are using our tool, they don't need to worry about the optical S parameters. They can easily extract the equivalent electrical S parameters of any optical circuit. Then OptiSPICE allows users to view the output signals in multiple formats and extract them for the post-processing in Python and MATLAB. OptiSPICE offers integration internally with other OptiWave tools like OptiSystem, allowing optical link post-simulation and leveraging devices and simulation capabilities of both tools. This integration allows users to integrate the chip or circuit level design into a system level circuit, and thereby allows users to actually see how their PIC is behaving at a system level circuit. Then we also offer external integration with third-party EDA vendors such as Siemens, and this will be discussed further during this webinar. OptiSPICE also offers compact model support by importing component-level devices parameters from OptiFT3D, where a user can extract the S parameters and feed it back into the OptiSPICE to run circuit simulations. Then we also have integration with OptiBPM, where a user can extract these parameters in the .bpm format, and we can create compact models for the waveguides and the complex shapes with the aid of OptiMode, where user can run circuit simulations based on the effective indices data file, and we can feed that into the OptiSPICE circuit to build your PIC and run simulations. OptiSPICE also allows to build PDK components and use them for PIC simulation and characterization. Currently, we support PDKs from VLC Photonics, LiDAR, and Fraunhofer HHI. Now, let me introduce you to two versions of OptiSPICE software. We provide OptiSPICE Standalone, which has its own graphic user interface and offers full solution for analog simulation of optoelectronic circuit and devices. It has a vast electrical and optical component libraries and also provides lots of detailed examples showing the capabilities of OptiSPICE tool and its component. Then we also offer OptiSPICE plugin, where we integrate the optical simulation capabilities into the third-party electrical EDA tools. We add on the optical models, which allow the designers and engineers to continue using their electrical EDA tools by leveraging the optical components provided by OptiSPICE device library. If we talk about the certain features of the tool, such as graphic user interface, then Standalone has its own graphic user interface, and the plugin in the plugin we use the graphic user interface from Siemens EDA. And if we talk about the visualization tools and electrical model library, for Standalone we have our own tools and own electrical model library, whereas in the plugin we use from the Siemens EDA. The optical model library for Standalone and plugin, we both for both tools we have our own device library. So even for the plugin, we provide our own optical models into the third-party EDA. For the simulation engine, Standalone has its own engine, whereas in the plugin we use a simulation engine with Siemens EDA. Then, if we talk about mask layout and DRC tool, for the Standalone, we currently don't have our own mask layout tool, but for the using plugin, we can use the mask layout tool from Siemens EDA. And if we talk about optical PDK compact models, Standalone and plugin both are capable of building the compact models. Now, we will discuss about a PIC example, which is designed and simulated using OptiSPICE plugin. This example is a LiDAR technology. As we already know, LiDAR is an acronym which stands for light detection and ranging. This technology is being widely developed and used in the automotive industry, inside autonomous vehicles for detection, inside drones, as well as in the atmospheric sciences for the detection of many types of atmospheric constituents. Now, first, let's talk about the principle and theory behind the LiDAR technology. It's a sensing technology that uses light in the form of pulse laser to measure the distance to the target. Here in this figure 1A, we can see that the laser sends the light signal, it hits the target and is reflected back, and the signal goes into the optical chip. And also the signal from the laser goes into the optical chip, and then the further processing of the signal is done to calculate the distance to the target. Now, this general working principle is being demonstrated in this webinar, where we have built a LiDAR chip. So you can see that we have a laser source which sends the signal into the optical LiDAR chip. And the signal from one end, the signal goes out of the chip, it goes and hits the target, and then it is reflected back and comes back to the optical chip. And then the further processing of the signal is done. Here, in this chip, we'll be using the building block compact models from HHI PDK. So the idea is to measure the target distance. So if we talk, once we receive the signal out of the optical chip, it's because of the combination of two signals, the signal within the chip and the signal coming from outside after hitting the target. So at the output, after the balance photo detection, we receive a beating signal, which is a sinusoidal signal. So using that signal, we can calculate the frequency period using this equation. And from that, we can calculate the wavelength of the sinusoidal signal. And then we can calculate the distance traveled by the sinusoidal signal in 1 second using this relation. Then we can calculate the time delay using this equation, where dt is equal to r effective times 2 times the length to the target over c. We have used twice the distance because we need to take into account the distance traveled by the light to hit the target and then when it reflects back. Then the total distance traveled by the signal outside the chip is given by ddt equal to dt times dsec. And this will give us the total distance. And then if we divide it by 2, we can get the actual distance to the target. Now, here's the design and simulation workflow of a LiDAR PIC using OptiSPICE plugin, which is seamlessly integrated with the Siemens EDA tools. So firstly, we will build a mask layout of the LiDAR PIC in the Siemens mask layout editor known as LEdit. So this image, what you see over here, is the schematic editor. So here we are using the building blocks from the HHI. So as you can see, we have a balanced photo detector. It has 3 electrical ports, ground signal, ground transmission, and it has 2 electrical ports, one on the top and the bottom. Then you can see here, these are some waveguide transitions. Then we are also using the bend waveguides, some straight waveguides, and this is a 2x2 MMI coupler. This is a 1x2 MMI coupler. And then we have spot size converters basically used to couple the light into the in and out of the chip. So these are the output electrical ports. This is the input optical port 1. So from here, we see the signal and then it's splitted, and one part of the signal is sent out of the chip to the target. So this is the optical output optical port, and then after hitting the target, the signal comes back here. So this is the input optical port 2. And then when these 2 signals are mixed here, it goes to the balanced photo detector and produces the beeping signal. So once you have built your PIC layout in the mask editor in LiDAR, then what you can do is extract the netlist out of it. So here we have extracted the netlist. This is, as you can see, it's a LiDAR chip, and it is in a sub-circuit definition. So you can see it has, in the first line, we have the ports. So it shows port 1, port 2, port 3. So these are the optical ports. And then these are the electrical ports. And you can see the list of all the components being used, whether they are the bend waveguides, straight waveguides, whether they are the balanced photo detector or the spot size converter. So all the components are listed here. And it also shows all its property. It tells about the waveguide length, overall length, and the configuration of other components. And then it also establishes the connection. So you can see here how these devices are connected to each other. So once you have this netlist, then you can use this netlist and build a sub-circuit component in the SEdit circuit simulator. This is again from the Siemens EDA tool. So this SEdit is basically a circuit simulator tool. So you can build the sub-circuit of this LiDAR chip in that. And as you can see here, it has 3 optical ports, 3 ground signal, ground transmission line, and then 2 electrical ports here. And then you can use this sub-circuit and you can build your test bench around it. So as you can see, we have this component here, and then we have used the other components such as laser. From our laser circulator, we have a waveguide to define the target to the distance, and then we have defined the target. So all these components are taken from our OptiSPICE device library, and all the electrical components such as the voltage sources, the probe visualizers, the resistors, and ground. So these are taken from the Siemens EDA device library. So you can see that here, the laser sends the signal into this input port, which is basically this port. It splits into 2, and from this output, the signal goes out. Here we have defined the waveguide, and the N effective for this waveguide is set to 1 because it's an AR medium. And we have set the distance to the target is 20 meters. So it goes and hits the target, and it is reflected back through this port basically, and then the further it enters into the balanced photo detector, and at the output we can retrieve the beating signal or the sinusoidal signal out of the chip. So this is the overall workflow from schematic, from using the building block components to build the schematic of your PIC, then extracting the netlist, building a sub-circuit component, and then using it for circuit simulation to characterize the performance of your PIC. Now let's dive into the tools and see how exactly it works. So this is the LEdit schematic editor tool. Now, first of all, we have to load the library definition file of HHI PDK. This is the library definition file. Give me a second. So this is the library definition file. So we load this library. Basically, this library definition file contains contains the definition or the information about all the building block components provided by the HHI PDK. So we need to first load this one. Once you select that, now in the library section here on the left, you can see under the HHI PDK device library, you can see all these components here. So it has like bends, 90-degree bend, 45-degree bend. We have DBR section, distributed feedback, electro-absorption modulators, and so on. They have MZI switch. So you have the list of all the building block components provided by the HHI PDK. Then the next step is to use these components, connect them, and build your PIC. So this is, I have already built this PIC for LiDAR. And this is the schematic. So as you can see, I have used the balanced photo detector, some electrical transmission lines. Then these are the optical waveguide transition. And then we are using some standard auto-generated waveguides, like straight waveguides, bend waveguides. And then we have, if I zoom in a bit, these are the MMI 2x2 building block. Then if we look at this, so we have MMI 1x2 building block. And then if we look at these components, these are the spot size converters for input and output. So this is how you just drag and drop your components, establish connections between them, and then your PIC is ready. You can, of course, you can do the DRC check. And if your circuit is DRC error free, then what you can do is, then once you have built your schematic, you can go to tools, go to photonic tools, and then hit extract netlist. Now here, let me tell you briefly about the header file. So this is a header file, which is, again, it's a text file which contains the sub-circuit information about all the building block components. To be precise, how these building block components are modeled, maybe using some S parameters, maybe waveguides are modeled using an effective data, like an effective as a function of wavelength or frequency, or how the electro-absorption modulators or Mach Zehnder modulators are modeled. So all the information is stored in this header files, and these components are in a sub-circuit definition. So this is important to select, because then it's gonna create a sub-circuit in the header file, and then we need to define the path for the netlist file which we want to extract. So in my case, let's say I'm using the desktop to save this netlist file, and then this is important to select write as dot subcircuit, because then it's going to extract the netlist of this entire PIC circuit in a sub-circuit definition. And that is what we are going to use later on to build the component. So once you've defined the path and everything, just hit OK. Now let's go. Yeah, so here is the file. Now let's open this. So as you can see, we have LiDAR chip. It is because we selected dot subcircuit, so it's now it has now created a subcircuit definition of this entire LiDAR chip. You can see the ports: port 1, port 2, port 3, and these are the optical ports. These are the electrical ports, and you can see the list of all the components and how they are connected to each other. So this tells about the entire PIC layout definition. Now, what we need to do is, once you have extracted your netlist, the next step is to go to the S editor. So this is the S edit, which is a circuit simulator tool of Siemens EDA. Then here as well, first step is to load the same library definition file. This basically contains the information about all the building blocks. So you select that, you hit open, and then once you open it, you will see a window like this. So on the left, you can see the device lab. You can see a lot of libraries here. So these are devices where it contains all the electrical components. Here you can see all kinds of resistors, inductors, NPN transistors, capacitors, and all the electrical components. Then you see the SPICE plot. Basically, it's a library for which contains all the visualizer and all kind of plot visualizer components. Then we have sources, voltage sources, DC, AC, V pulse, current control, current source, and all kinds of voltage sources which you can use. And also, we have our OptiSPICE device library. So this is the library which we have added to the Siemens EDA. This basically contains all the optical components, and thus it allows users to build their electro-optic circuit and characterize them. So here you can see we have some electro-optics, some nonlinear components such as lasers. We have a frequency control laser. We also have an electrical filter. We have optical filters. We have all kinds of optical components like optical gain, isolator, phase shifter, different waveguide types. We have waveguide crossing, waveguide phase shifter, and so on. Then we also have S parameter components wherein user can use any S parameter extractor tool, any of the tool to and they can extract the S parameters using that tool, and you can use those S parameters in a custom format and feed that into this component, and you can run the simulation for that. So this is the device library provided by OptiSPICE. And then it also comes with some standard OptiSPICE circuits, which can give you a good starting point to build your circuits. So now what we need to do is the first step is to create after extracting the netlist, first step is to create the subcircuit component here in SEdit. So for that, what we need to do is I select here, select new view. Now it'll ask you where you in which library you want to save your component. So let's say I'm saving it in HHI circuits. Then we have to define the name. Let's say LiDAR chip test 2. And then we need to select the SPICE because we need to define the SPICE definition. SPICE, and hit OK. So now you see here it's an empty block. Now what we need to do is this netlist, what we extracted out of LiDAR chip, we need to just copy paste it here. So once you have done that, then you go to cell, and then you create generate symbols. Now, it again is going to ask you for the library. We are going to save it here. cell name is selected. The view currently is SPICE, but now we're going to create a symbol out of it. So then we need to define the ports. We need to define the port placement by name. So on the left side, we have, let's say, G1, S, G2. Right side, we have optical ports, OPT1, OPT2, OPT3. On the top, let's say we have N. On the bottom, we have P. So we have defined the ports now, and let's hit replace. So here, now we have generated a sub-circuit component of the entire LiDAR PIC. You can see on the left, we have ground signal, ground transmission line. We have ports, and we have N and P ports, electrical ports on top and bottom. And on the right, we have optical ports. Now, if you observe closely, these optical and electrical ports, they look similar. So what you can do is just to have a different visualization of these ports so that you can distinguish them separately. We select it, we select the type, and we hit photonic. Now you will see the port looks different. So you can do that for all of your optical ports, basically. And now your component is ready to be used in a test bench. Then next step is to create a test bench. Now, let me quickly go through. So first thing you will have is like an empty schematic. Now, what you can do is we need to build a test bench. So here is a symbol. We drag and drop here. So this is the symbol. Sorry, this is the circuit. Let me just use the okay, font size, maybe 6. Yeah. So now this is your LiDAR chip. Now we want to connect devices around it. So let's say we select OptiSPICE device library, and from there we select frequency control laser. And then we need to drive this laser. So we need a DC source. We select that, and then we establish connections around it. And yeah, so this way, and then you can connect the laser to the input here. So this is the optical port. So we are connected to the laser and so on. And then you can just simply drag and drop the components and build your schematic. So so this is going to take time. So I've already built it. But if you see here, there's a color basically, there's a color coding. So for all the optical signals, you can see they are highlighted in orange, and the electrical signals, they are highlighted in blue. So now let's go ahead and see how the test bench looks like. I have already built this schematic. So here is the LiDAR. Here's the LiDAR circuit, and we can see that we have used all the components like laser. We have a circulator outside the chip. We have a waveguide and the target. And to drive the laser, we have voltage sources. We have used the voltage probes to measure the signal out of the balanced photodetector. So we have already built this schematic, which we have discussed earlier. And now, once you have built your circuit, then, okay, before that, let me show you. So here's the laser. So this is how you can set the parameters for your components. So in the channel value, I've set the frequency to 193.1 units is terahertz. We are basically, so this is a frequency control laser. So we are using a voltage source here to ramp up the signal from 193.1 to 193.11 terahertz. And we can set the fall time, rise time, we can set the period. And if we talk about the waveguide, we have set the length to 20 meters. So this is basically the distance to the target. And we have set the refractive index of this waveguide to 1 to basically show that it's traveling in air. And we, during this simulation, we are assuming that there are no losses and no dispersion or anything. So kind of we are simulating an ideal scenario. Then once you have built your test bench, then you can go to settings, and in the general here we need to select that header definition text file. It's important because then user will know the Siemens EDA knows what component is what. And so once we define that, then we go to the transient analysis because we are going to run transient simulation. So we set the stop time, it's set to 200 nanoseconds, and then that's the maximum time step. And once you have defined your setting, then you just hit run simulation. I'm not going to run it now because it's going to take a long time. So I've already run it before. And once the simulation completes, then here is it opens the Tanner waveform viewer. This basically shows you the results, the plots. This is on top, we have N3 probe where you can see that your frequency is being ramped up from 193.1 terahertz to 193.11. The rise and fall time was set to 100 nanoseconds. So you can see the ramp signal. This is the signal. N6 is basically the signal coming out of the photodiodes. And as you can see, there is a time delay because of the distance traveled by the light to the target and coming back. And if I just zoom in here, you can see here it's the sinusoidal signal. So this is basically your beating signal, which you observe from the combining of the signal coming directly from the laser and signal propagating to the target and coming back. So that's your output signal. Now, once you have your output signal, now this is the zoomed in response, what we are seeing here of the signal. Now using this signal, we have calculated the period of the sinusoidal signal, which is around 0.1498 nanoseconds. And from that, we calculate the frequency of the signal, which is around 6.67 gigahertz. Then we calculated the wavelength, which is around 44.9 millimeter. And the time delay outside the chip is calculated to be 133.426 nanoseconds. And using this, we have calculated the distance traveled by the signal for time dd outside the chip, which is 40 meters. And then we divide this distance by 2 because we need to counter both the light traveling to the target and after reflected back. So we divide by 2. So it comes down to 20 meters. And this was the length which was set in the waveguide in the simulator. Now, so this was basically the overall workflow of how you can build your PIC. In this particular case, it was a LiDAR example. So how you can build your PIC in using schematic editor in LEdit and use the components from a foundry or maybe your own mask layouts, build your mask layout, extract the netlist, use that netlist to build a sub-circuit component, then use it for circuit simulation and characterize the performance of your PIC. Now let's discuss how we can build and simulate the LiDAR circuit using our OptiSystem tool. And there are different methods to simulate distance to the target here. I'm going to discuss only 2 of them. In the first example, we detect the distance to the target using the time of flight. Using the time of flight here. In the schematic, we see a Gaussian pulse generator, which sends a Gaussian pulse, which is modulated, and then it is transmitted to optically to the virtual target. So here we have defined a virtual target. Basically, we have added a delay here, and then it hits the target, and then it reflects back, and then it is received by a photodiode, and then we do some amplification, and then the signal goes to the C++ component here. This is basically a constant fraction time measurement. Now, what happens inside this constant fraction discriminator is that first makes a copy of the received signal, it inverts it, and then applies the delay. So the original signal is then reduced in amplitude by the factor of CFT fraction, and summed with the copied signal waveform. From here, this is basically a processing unit. It processes the signal, and then it shows the signal in the oscilloscope. We have named it constant fraction signal. So here you can see the signal coming out after the processing, and basically, yeah. So that's the overall circuit, and these are the different parameters. Here we have a safety delay, safety fraction, and safety noise threshold. The sensitivity of this constant fraction discriminator can be modified by changing the input parameters, these parameters here. Then these are the global parameter settings for LiDAR system. Here we have set the range to 750 meters. And the range of the target is calculated basically using this relation, where we have a time of flight times c over 2, and c the speed of light. This time of flight is the time taken by the laser pulse signal to travel from the transmitter to the target and then back to the receiver. And the received signal power is determined based on an extended target model and is calculated using this equation, where PT is the transmitted optical power, D is the receiver aperture diameter, rho is the reflectivity of the target. Then we also include the atmospheric loss factor and the optical transmission system loss factor, and R is the target range. So this gives us the power received, power of the received signal. Then you can see here in the constant fraction time signal, the received pulse is time triggered at 6.02 microseconds here, basically, and this gives the range of around 751.27 meters. So what this C++ does is it reads that time, and then based on this time, it calculates the range here, 751.27 meters, which is in close proximity to the range set in the global parameters. So this is one way of designing and simulating your LiDAR system by using time of flight. Then the other method is by using the coherent detection. This is the setup. So here, frequency modulated. Here we have basically linear frequency modulated waveform generators. This is a subsystem which sends the signal, and which is split into two. It goes to the transmitter, and from the transmitter it goes and hits the target. Again, we have modeled the time delay here for the virtual target. Then when the signal is reflected back, it combines with the signal from the transmitter before entering the balanced photo detector. So since it's a coherent detection technique, we are using a balanced photo detection. And after the balanced photo detector, the signal is combined with the signal coming from the waveform generator, the original signal. And then after the mixing, the signal passes through a low pass filter to filter out any unwanted noise of the signal from the output signal. And then the signal goes to the C++ component, which is basically, again, it's a processing. The signal processing is done. So here, what it does is it measures the beat frequency, which is 149.9 megahertz. And then using this beat frequency, it calculates the range, estimated range to the target. Now, the relation to use the range using the frequency detected is given by this. So here it's given by RF times C times the ramp period over 2 into delta frequency. C is the speed of light, RF is the frequency, the detected RF signal, which is measured here, and the ramp period is the global parameter in the time window. And the delta frequency is the parameter set in RF sweep bandwidth in the subsystem, in this subsystem here. So once the frequency is detected by the C++, then it calculates the range. And in this case, the range is coming out to be approximately 749 meters, which is again in very close proximity to the global setting of 750 meters. This is basically the signal. As the received signal is like time delayed, so there is an intermediate frequency signal which is produced here, which you observe here, and the frequency of the signal is 149.9 megahertz. So in OptiSystem, we show two detection techniques to calculate the distance to the target. The difference between both detection systems is basically the one uses square law detection, whereas the other uses a coherent homodyne detection to recover the incoming optical signal before mixing, and then using that we can calculate the range of your target. So now if you're looking for other applications or information regarding our products and how they can be useful for shaping your imagination into reality, there are two primary sources you can check. We have a knowledge base, where we have articles based on the fundamental theory, we have articles based on the structures without paper confirmation, and also the reproduction of some of the research papers or publications. And we are growing the number of articles with time. Also, you can check out our YouTube channel, OptiWave ST, where you will see a wide range of webinars and tutorials for all of our products. For the PIC designing, you will see OptiSPICE, also OptiSystem, and there is a playlist for each product, and you can go through it. And this will help you to get started with our tools, and it can help you to build your PIC as well. And with that, I end this webinar. I hope it was very helpful for and very informative for you. So if you have any PIC design and simulation needs, please reach out to us. You can directly reach out to me at my email address, or you can reach out to us for more information about the products at support@optiwave.com. And with this, I would like to end the webinar. If you have any questions related to this PIC design simulation, please reach out to us. And you can always download and install a free 30-day evaluation license for all of our tools. You can register using your professional email address, and you can install the tool and try it out. And if you have any questions, please don't hesitate to reach out to us. So, and regarding this PIC webinar also, if you have any questions, we are more than happy to take it. So with this, I would like to end this webinar. Thank you very much for attending it.